All right, welcome to the Smart Buildings Academy TV episode 2. And in this episode, we are going to be talking about IT networks, and we're going to be doing a live question and answer session as well. My name is Phil Zito, the founder and CEO of Smart Buildings Academy. We are the fastest growing provider of online training for building automation professionals. Okay, so when I start to teach IT networks to a lot of our students, where I see them getting tripped up is in some of the basic IT networking concepts. So in this episode, we are going to be talking about LAN topologies. We're going to look at subnets. We're going to talk about some basic IT networking terminology. We are going to look at how backnet traffic can travel across subnet boundaries and within local area networks. And then with the time we have left, we will do some live question and answer. Please familiarize yourself with the discussion tab below the video. That's where you'll be asking questions. I highly encourage you to ask questions throughout this. The engagement will make this much more enjoyable for all of us, especially at 8 p.m. at night. All right, so when we're talking about a network, one of the big issues I see with folks, especially when dealing with IT, is not properly communicating in IT's language. So the first thing we want to focus in on is network terminology. So with a local area network, we'll have a layer 2 architecture. In this case, we have a switch, and that switch is using ports to connect to hosts. So your BAS device is nothing more than a host on a IT network. It's a host that is utilizing resources on the IT network, both physical resources in the form of access links and switch ports, and logical resources in the form of IP addresses, things like that. So when we are connected on a local area network, we have our switch, we have our access link right here, which is allowing us to access the network. And that switch has a physical port, and that port connects to a network interface card on our BAS device, also known as a NIC. Now, I'm not going to get into the 3 different architectures of IP controls. We are primarily just going to be looking at the star pattern here, which is the one-to-one end run, although there are other patterns. Now, on the upside, when a switch is trying to connect to another networking device, it utilizes what is known as a trunk port, and that allows it to trunk between networking devices. Now, a router is often used in order to connect us across subnet boundaries. So a subnet is just a sub portion of a greater network. And we utilize it because in IP addressing, we have IP address limitations, and subnetting allows us to recover that. So this segment right here, just this, I'm going to make some dots here. Just this little segment is considered a local area network. However, this local area network may consist of multiple subnets, and we'll get to what a subnet is and an IP address in just a second. So we've got this router right here, and it is allowing us to segment network segments. So we have a switch, in this case switch 1, and we have a switch over here, in this case switch 2, and they're connected via the trunk ports by the router. And then maybe we have another BAS device down here, which we'll just call BAS2. And we've got our access port, our access link, and our network interface card. We can see those right over here. All right, so how all of this works is you have these physical addresses and logical addresses. So the physical address, in the case of our BAS devices, is going to be known as the Ethernet MAC address. So very similar to MAC address on MSTP devices, except in this case, it's using hexadecimal, and it is for Ethernet protocol, not for MSTP. So the MAC address acts as the physical address for the device. It is unique to that device. Now what happens is inside a switch, it has what is called ARP, Address Resolution Protocol. An address resolution protocol seeks to identify the logical address, which is an IP address, and it seeks to match the logical address to the physical address. So an ARP request is sent out to any devices on the local area network, and these devices respond to the switch, and this happens usually every 5 minutes, and the ARP table is built, and it will say port whatever, and that is this MAC and then this IP, and it'll build that. So maybe it's like port gigabit 1. And maybe that's MAC, FF ... and IP address, 192 ... I'm saying ... because I'm not writing out the whole address just because of space. Well, it builds this all out. And that is how all of our layer 2 messaging communicates. Layer 2 messages are things like broadcasts, which are incredibly important in BACnet, which we'll cover in just a second. Now for IP traffic, which is the logical address for these devices, IP traffic is going to be how we address these machines, these devices, so that they can communicate logically across both the network as well as across multiple subnets. So let's get into what an IP address is and what subnets are. But I'm going to pause before I erase this and see if there are any questions around logical area networks, switch ports, switches, routers, etc. We will come back to routes. We are going to describe subnets, and we are going to close this out with how does BACnet data travel across a network. But seeing no questions, I'm going to move on to talking about IP addresses. So we have two types of IP addresses. We have V4 and V6. We're primarily focused on V4 addresses, and these are 32-bit addresses. So if you're familiar with MSTP and the MAC address, then you understand what an 8-bit address is. Remember those dip switches that we need to flip, and they're either an on or off state, and we add those up and they can equal whatever the MAC address is? Well, IP addresses are kind of like that. We have 4 8-bit arrays known as octets, and those bits represent these addresses or these numbers that I'm writing on the screen right now. 128, 64, 32, 16, 8, 4, 2, and 1. And so when a bit is turned on, that represents, so it's either a 1 or a 0 for the bit. When it's on, we add that number. So if I were to show you something like this, 1, 0, 1, 0, 0, 0, 0, 1, we would add, 128 plus 64, that's 192 plus 1, that's 193. And so that's how we get our first address. And an IP address is 4 octets. So it's x.x.x.x. And you can see I already got one of the x's right here by adding these up. This becomes important when we start to think through subnetting. Now, you've probably ran into a scenario where you've asked an IT group for some addresses, and you said, hey, can you give me a /24 subnet on 192.168.1.0? And you've been taught that by maybe your senior tech or someone saying, hey, this is what you need to ask for. And sometimes IT looks at you like you're a little crazy because you say, hey, I need 8 IP addresses. Can you give me a /24 subnet? And what they're hearing you say is, you need 8 addresses, but you're asking me for 254 addresses. So what's going on? Well, remember that 32 bits? Well, /24, known as CIDR notation, tells us that 32 minus 24 equals 8. Where did that come from? We have 32-bit options here, right? 32 bits, 4 sets of 8. Now, /24 means that 3 of these octets are allocated to the network. These are network bits, meaning these are used to identify the network. And this last octet of 8 octets, which 2 to the power of 8 is 256, is the host bit section, right? So host. So what that means is that we can give 256 host addresses. Now, the problem with that is it's not exactly true because we can only do 2 to the power of 8 minus 2. And I'll explain to you why we subtract the 2 in just a second. But you can see right here, 24. So 32 minus 24 equals 8. That's how we got this 8 right here. So minus 2 comes from the default gateway and the broadcast address. So I'm going to draw a much smaller version of the network up here kind of in the left-hand corner a little bit. So we've got a router and we've got 2 switches. Now, the default gateway is where IP traffic goes when it's not on the local subnet. So if I told you had a 192.168.1.0/24 subnet, and you were trying to communicate to a 192.168.2.0/24 subnet, your local network, your local subnet could not communicate. It would need a default gateway that then would have routes to that other subnet. Now, the broadcast address is where all messaging goes for broadcasts. Now, there's 3 types of IP traffic. There's broadcasts, unicasts, and multicasts. We'll come back to this when we talk about BACnet in just a second. But broadcasts are messages that are sent out to everything on the subnet. So backing up a little bit now that we kind of understand IP addressing, if we go back to our diagram here of a router, 2 switches, we're just going to call it switch 2 and switch 1, and then BAS 1 and BAS 2. Now, if BAS 1 wants to communicate to BAS 2, and BAS 2 is on subnet 2, and this is on subnet 1, then what has to happen is in this router, there needs to be a route that says, oh, to reach subnet 2, you go out this port. Now, if we want a broadcast to reach subnet 2, there's really nothing we can do. And you say, but Phil, there actually is. And that's with BACnet. And I would say to you, yeah, you're absolutely right with BACnet, but IP traffic in and of itself, broadcasts are not going to travel. And the reason why is, imagine I initiate a broadcast on subnet 1, and it's able to be forwarded to subnet 2, subnet 3, subnet 4. It crosses these subnet boundaries. Before you know it, everyone in the world who's on the internet is sending broadcast messages all over the world and totally overwhelming networks. That's why we have broadcast boundaries, and we cannot send broadcasts outside of our subnet. Okay, so our broadcast cannot leave our subnet. Now with BACnet, that's not necessarily true, and we'll talk about that. Now, as I mentioned, we have default gateway. Default gateway can be any address in the subnet range, although it is usually the first, and the broadcast address has to be the last address in the subnet range. So doing a little bit of subnet math again, if you were asked that scenario of, hey, I need to ask IT for 8 IP addresses, what you could do is you could remember that 128.64.32.16.8.4.2.1 bit register, and you could say, okay, what can I do? Well, maybe I could go with an 8, right? You could say I need an 8. And the problem with selecting 8 on that bit register is, remember, 2 hosts go to default gateway and broadcast address. So you would need to go the next one, which would be 16. So 16 to the power of 2, right, is going to be, if I remember correctly, it is going to be, so 2 to the power of 2 is 4, 3 to the power, it's going to be 4. So we know that we need 2 to the power of 4 to get 16. So 32 minus 4, that is going to equal 28. So we would be asking for a /28 network. Now, there's much more to subnetting than just this brief example, but I really just want you to be familiar with CIDR notation and what all this stuff means. Now, let's go into this BACnet example and see if we can illustrate all of this in a way that makes sense. So oftentimes, I will run into people who are trying to do BACnet discovery. So we've got a BACnet device here going into switch 1, and we're going to say it's on 1.0/24 subnet. And it's going into a router. And we got switch 2 over here. And we got BACnet device 2. Right, BACnet device 2. And it is going into a .2.0/24 subnet. All right, so different subnets. Now, how BACnet works is it uses 2 broadcast services, and then the rest of its services are primarily unicast and multicast, meaning they're one-to-one or one-to-many, whereas broadcast is one-to-all. So in order for us to do our 2 broadcast services, which would be the who is, I am, and the who has, so we're just going to put who and has. So the first thing that happens, right, the BACnet device, when we do a discovery, it's going to send out the who is, and it's going to get an I am reply. And it's going to build a backnode list, right? It's going to build a list of BACnet devices. And those devices are really the IP address plus the device ID. Now, once it has a list of devices, it is then going to query using who has, I have, and that is going to build the object list under each device. And so that's how, when you do a BACnet discovery, that's what's going on. You are doing a list, right? You're building out this list of BACnet devices, and then you are doing this has discovery of all of the objects under each individual device in the list. Now, it's all well and good for .1.0/24 subnet, but there's no way for that broadcast to reach .2.0/24. So we're kind of up creek without a paddle because we can't do that. Enter the BBMD and BDT. Now, the BBMD is the BACnet Broadcast Management Device, and it has a BACnet broadcast definition table or distribution table. I don't remember off the top of my head here. But each BBMD exists on a subnet, and it has a BDT of all BACnet networks. Okay, so BDT for this BBMD, BDT for that BBMD, and the BDTs tell the BACnet network where to send their distributed broadcasts. Now, this functionality, a lot of people get this mixed up. They think that BBMDs and BDTs are used for all BACnet traffic, and that is not the case. BBMDs and BDTs are only used for these broadcast services. Once we build out this BACnet list and this object list, unless anything's changed, we're going to be using unicasts and multicasts for our read property multiple, write property multiple. And remember, unicast messages are going to go to the BACnet device, the BACnet address, which is simply the IP address plus the device ID. Now, the important point to know here is this IP address and device ID, since it's a unicast, it will simply use the route that is in the routing table. It will not worry about this broadcast message. So this BACnet device over here, once it has discovered this device over here and its objects, it can simply send a read property, and the default gateway will receive that because it's for a different subnet. It will then get sent to the switch, which will use the address resolution protocol to figure out which port to send it on, and it will send that encapsulated IP message encapsulated by an Ethernet frame to the BACnet device, and then it'll go back up the OSI model layer. Now, there's one more kind of wrinkle in all of this, and that is the ports. Not to be confused with physical ports, we now have logical ports, and these are layer 4. So layer 1, and I'm talking OSI model when I say layers, layer 1 is the physical. It's the wiring, it's the signaling, etc. Layer 2 is the data link. It's the literally the linking for exchanging of data on a local area network. Layer 3 is the IP layer. That's literally the IP traffic, and the network layer is actually what it's called sometimes. And then we have layer 4, which is the transport layer, and that's where we have our ports, and that would be like TCP ports and UDP ports. Well, BACnet by default is BAC 0 port. You'll hear it called like BAC 0, BAC X 0, something like that. It's 7808. Now, back in the day, we used to be really resource constrained on our networks, and folks would be like, oh my gosh, How can I go and have this massive campus BAS network and not overwhelm my networks and my traffic and blah, 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 blah. So they would implement multiple ports. Now, that's not really the case anymore. The thing is that our traffic, anyone who tells you BAS traffic is going to bog down your network doesn't know their head from their ass. I mean, they really don't, because if they did, they wouldn't say that. The reality is that BACnet traffic is so light. It is like so light compared to regular like AV traffic, big data dump backups, things like that. BACnet traffic is so light and its packet size is tiny. And so BACnet nowadays is not going to do anything. Honestly, you're more at risk of having someone maybe like hang a 4K camera off of a BACnet IP device that has multiple ports, and then that AV traffic overwhelming your trunk ports than you will ever be of your BACnet traffic overwhelming. Anyways, though, you're going to come to some job sites that have one set up as port 47808 and another set up as like 47809. And this is where routing needs to take place. And in your routers, you will say, okay, we need to route to this port as well as this IP address. So it's a very simple fix, but if you're not cognizant of it and you go to troubleshoot and you're like, I'm pinging 47808, but I'm not getting any traffic, that would be why. And it's just a matter to realize that you have routes and things like that. All right, I know that we were like kind of all over the place, but a lot of stuff for us to cover. This was just a primer. If you are at all interested in information technology, I encourage you to check out some of our courses at courses.smartbuildingsacademy.com, especially this Friday when we're having our Black Friday sale. With that being said, I want to enter into the question and answer session, so feel free to ask any questions you want. There will be a little bit of a lag between that because of the live stream usually runs about 20 seconds behind what everyone else is seeing. So definitely understand that. And we will go and answer the questions as soon as they come in. And I always like to go directly to my channel. I like to check it kind of here, make sure I am seeing the latest questions in case something came through on the back end. All right. So I will answer a couple common questions that I get while I wait for you all to ask questions. The first would be, what are those three architecture types I referenced? One of the things that a lot of people, so I spoke at Honeywell Momentum back in 2018. Man, it seems like ages ago. And I taught on IP controls. And someone asked me, man, what's the value prop for IP controls? And I started to tell them, I really wasn't 100% sold on IP controls. Nowadays, I am sold completely on IP controls for unitary equipment and above. I'm still not completely sold for terminal units, but for unitary equipment like fan coil units, rooftop units, and then obviously air handlers, chilled water units, hydronic hot water units, I'm completely sold on utilizing IP architectures. And here's why. Let's say you go to a commercial office building. It used to be that at the commercial office building, I would have to put in a supervisory device, and this was like around 4K after licensing. And then I would have my field controllers, and everything would be kind of good. And sometimes the supervisory device would have graphics capabilities. Sometimes I would have to put a client on top of it, or maybe some sort of server. But nowadays, with an IP controls architecture, what I'm able to do is I'm able to take, like, for example, I have the Cyper 10s, which are what we're teaching on now in our courses. I have the Cyper 10s sitting behind me, and they have an MSTP bus. I may be mixing these up with a Cyper 50, so you have to forgive me. It's a little late at night. But the Cyper 10 has 4 ports, IP ports on it, and has an MSTP bus. So what I would typically do is I would put this on the rooftop unit, and then I would use MSTP to all of the terminal units. And then I would put the graphics and everything on the Cyper 10. It's a substantially reduced cost. But there's 3 IP architectures that we can implement. So what I could do with all of these IP controllers, let's say I have 10 rooftops. I could go and have 10 different controllers all home run to a switch. And that's going to be rather expensive. I'm usually paying per port to IT in order to utilize their switches. So that's going to get a little bit pricey. So the second architecture actually is to go and do a daisy chain, which you can do with IP controls, just like with MSTP. Now, the problem with this is a lot of IP controls do not have physically bridged network adapters. So what that means is that if I lose power to this IP controller right here, then I am going to lose the ability to connect to this controller as well, because electrically the signal will not continue. It's not like RS-485 where you can lose power to a controller and the signal is just going to continue on. Now, a lot of manufacturers are starting to recognize this and they're starting to address this, but it's still something to be cognizant of. Which brings us to our, this is star, this is daisy chain, and then this is ring. Brings us to our third architecture. Our third architecture, and these are the switches, by the way. Third architecture is a ring. And so it's very similar to daisy chain, except it goes back to the switch. So that if I lost this controller here for power reasons, my controller would see this, or my switch would see this, and it would turn on this port as well, and I would be able to hit this controller. And it does that through a technology called spanning tree protocol and rapid spanning tree protocol, which we're not going to cover here, but we do cover in our IP networking and design bootcamp.